All right, folks, we are still in chapter 6. This is section 6-1. This is video number 2. Okay, so I really strongly urge you to spend the time reading this little section here, these paragraphs about the so-called normal distribution, okay? And make sure you understand the concept here. This is the mean of the distribution. This is plus 1 sigma. This is minus 1 sigma. Plug in some numbers, do whatever it takes to kind of get the idea of this, okay? It's going to be very helpful later on when we start talking about a variety of topics. Okay, so now, as the author says here, if you have a normally distributed random variable, it's going to have its own mean and it's going to have its own standard deviation. Therefore, the shape is going to be different. We saw that a few moments ago when we talked about the different mu's and the different sigmas. If you have two different distributions and they have a different mu, it's going to shift it from one, left to right. If you have a different standard deviation, it's going to change the shape of the distribution. Well, that makes it hard, right? Because how are we going to figure out what we need to know? We surely do not want to use this formula that's up here, which I can't find. We surely do not wish to use this formula. It is way too hard. Now, I want you to keep in mind, just for the sake of this discussion, that we could use that formula. There's nothing wrong with using that formula. It's a perfectly legitimate formula, but it's just too hard. So that's why we don't use it. What really happens is there are tables in the back of the book that will give us the information that we need. And at first, these tables look very difficult and are confusing, but trust me, if you just do a dozen problems, you're going to be able to use these tables very easily. Okay, so what's going on here then is we're going to use a table. We're going to use a table to answer all these questions. We cannot have a different table for every single random variable. That wouldn't make any sense. For example, you might say, well, the normal distribution for women's heights is 5 feet. So here's a I'm sorry, let me say that again. So what you might say is here's a distribution of women's heights. The mu, the average, the mean of the women's height is 5 feet 6 inches. Okay, you'd have to have a separate table for that particular distribution, for that particular mean, and for that particular standard deviation. You'd have to have a different table for IQ. There's any number of examples. So that wouldn't make any sense whatsoever. So what we are going to do is we're going to have another distribution. We're going to call it the standard normal distribution. So what's the difference? The word standard. The word standard here, what that tells us is that it's a normal distribution, but this particular distribution has a mean of 0 and a standard deviation of 1. So what the magic of this is that if you take any normal distribution, you can transform it into a standard normal distribution. Once you transform it, you then can use the tables that are in the back of the book. So stop this video, rewind a few seconds, and play that again. What we're doing here is we are transforming these messy normal distributions that have all the different mu's and all the different sigmas, and we are going to transform them into a well-behaved standard normal distribution. And the beauty of this is that the answers you get from the transformed standard normal distribution are exactly the correct answers that you would have gotten if you had used that formula on the original normal distribution. Okay, so how do we do this? How do we make this transformation? Okay, the formula for the standard normal distribution is this, and I'll let you look in your own book. You can compare that to the distribution for the regular, the normal distribution. The normal distribution, it has a formula. This is the standard normal distribution. It has a different formula. So it's a simpler formula. However, we still are not going to use this formula. It's still too hard. What we're going to do is we are going to use a table. So here's a key concept right here. All the normally distributed variables can be transformed into the standard normally distributed variable by using the formula for the standard score. So we call that a z-score. The z-score is value take away mean. What he's talking about here is the original value. Let's use the women's heights just as an example. Every value, Mrs. Jones is 5'3". That's her value. Mrs. Smith is 5'4". Mrs. Garcia is 5'2". And you just keep on going. You have all these values. Each one of those x's, each one of those random variables for everybody that's in your data set is transformed. You take that guy, you take the original guy, you subtract mu. Mu is the mean of the original distribution. So using the women again, the women's heights have a certain mu, and what you do is you transform each of the individual data points by subtracting the mu of the distribution. And we'll get examples here in just a second. And then what you do is you divide by sigma. Well, what sigma is that? That's the standard deviation of the original data points. So the author doesn't use this terminology, but many authors do, and you'll hear this in industry or what have you, is you have the original data, okay, and that original data is transformed into the Z data, okay? So you're transforming, you're going from the original data to the Z data. It's just a convenient way of thinking about it. Okay, all right, so now what he's saying here is we don't really care what the Y value is. So you're never going to see a chart that gives you the actual values of the Y axis. We just don't use them. What we use is the area under the curve. The area under the curve gives us the probability that we're going to be looking for. Okay, so here's his example. It's the area under the curve that such as finding the percentage of adult women whose height is between 5'4" and 5'7". Or if you want to talk about it in terms of probability, it's the probability that a new battery will last longer than 4 years. So what we're going to do is we're going to talk about how do we find this area under the curve. And I swear, once you see a couple of examples, it'll be more clear. Okay, so the x values are transformed. They're called z values. This is a transformation. In a more advanced math class, what you would say is that there's an isomorphism between the original data values and the z values. And what that means is that you can do stuff, you can do operations, and you can do things to the z values, and it's equivalent to doing it in the original data space, or the original x values. Okay, all right, so he talks about the table, so we'll see that here in just a little bit. We're going to use that shortly. Okay, so here's finding the area. Here's how do we find this area. So he kind of walks you through finding the area first before really explaining or showing you why this is important. Now, based on my experience, this is a hard area for whatever reason. I don't know why, because once you know how to do it, I swear it's just like riding a bicycle, okay? So what I recommend you do is pay attention to what I'm saying, read the book carefully, do the examples, but this would be really a good time to Google this or go to Patrick JMT and find some examples. They'll walk you through 3 or 4 examples step by step by step. It will make things a lot more clear, in my opinion. That's my recommendation. Okay, so here's the procedure table. Now what you're going to find is in the table in the back, they have a cartoon that looks just like this. What you need to understand is that it's too hard to make a table any other way, is what it boils down to. So the way we make these tables is they're going to give you a z value. Here's the z value. And then in the table itself, it will give you a number, and it will tell you what is the area under the curve to the left of the z value, okay? So if you want to find the left of any z value, we'll see here in just a second how you do that. You find the z-value, and then the table itself gives you that area to the left. The most important fact about all this is that that area to the left is exactly what we're looking for. It's the probability of something happening. So that's the probability that you're looking for. So you have positive z and you have negative z's. Now, if you wanted to know the right of any z-value, let's say you wanted to know what's the probability of something being bigger than some other number. So like, what's the probability that the battery is going to last more than 4 years? Well, you transform that 4 years into a z-value. Here's the z-value, and you find the area to the right of that particular z-value. Well, that's not in the table. That is not in the table. Okay? So what you do is the following. Okay, remember up here I said that every z-value, it gives you the area to the left. So if you want the area to the right, what you do is you find the area for that particular z-value right there. You find that area to the left, and you subtract it from 1. Because remember, this normal distribution, or this standard normal distribution, is also a probability distribution. We'll learn that here in just a minute, but I'll tell you in advance. It's a probability distribution, and therefore the entire area under that curve, it all adds up to 1. So if you want this area right here, what you do is you find the area to the left and you subtract it from 1. So let's just say, I'm going to make this up. Let's say at this point right here, you don't know what the area is to the right, but you know what the area is to the left. Suppose the area to the left is 90%. Okay, so there's a 90% chance of it being to the left. So then you say, okay, fine. If there's a 90% chance of being to the left, it must be a 10% chance of being to the right. Okay? The same basic concept applies here if you're trying to find between two z-values. If you're trying to say, well, what's the probability of, you know, I don't know, whatever it happens to be, like somebody being between the ages of 25 and 18, you know, that's your raw data, that's your X data. That's your original data points. You transform that into z-values, and if it works out this way, where between 25 and 18 is between here and here, well, what do? Well, it's the area to the left of that number, and then the area to the left of that number, and you just subtract them. Okay, so you look at both of the z-values and you subtract the corresponding areas. So that's just. Your intuition should tell you all of this, because you're just dealing with areas. So, you know, how much of an area do you have to the left on each of these will give you what you need to know. Okay. All right, so this is very important. This table, it gives you the area under the normal distribution curve to the left of any z-value. Okay, so that's what you need to keep in mind. It's to the left. And there's a cartoon. If you look in your book, at the very bottom of the page, there's a little cartoon that's going to look just like this one right here. That's to remind you that that's what it's giving you. So what will happen then is that you're going to find a table back there. Look in your book at the table, and this column right here, that's your z-value. So it's 2 decimal points. So let's say you wanted the area for the z equaling 1.39. So you go over here, 1.3, and then you go across to that second decimal place, which is 9. So it's 1.39. Boom, it's right there. Okay, so real quick, I got the book, the PDF book. So 1.39 is what we're looking for. So what do? Here's the table in the back of your book. Here's your z-scores. You come down here to 1.3. Then you go over here. It has the second digit. That's the 0.09. So 1.39 right there, 0.9177. 0.9177. That's exactly what we got. So what that's telling you is that the area to the left of 1.39, that area right there, that area is 0.9177. So if that corresponded to something or another, you're interested in probabilities, what you say is, well, that's a 91 point blah, blah, blah percentage or probability of being to the left. So that's how you use the tables.